individuals, but still I'm working on this topic. So I just want to change the title into like first step on molecular MIMO. And that is the joint work with my grad student and postdoc, and also joint work with Andrew Ackford. So, since I'm also a junior faculty, so I just want to have just 1 minute to introduce myself and introduce my research group. I got my PhD from the UT Austin under the supervision of the Robert Case. I did very short postdoc at Harvard University to work with the Bahi Charbo. And I'm now an assistant professor at Yonsei University in Korea. And I have 7 years of the industry experience, 2 years at Bell Labs and 5 years at Samsung. But mostly I was involved in like the communication systems like LTE, LTE Advanced, Massive MIMO, Small Cell Network, and so on. And this is the research group. I have the 1 postdoc working on the molecular communication, and 4 PhD students, and 3 the master student, and 2 undergrad interns. And the postdoc and 1 PhD student, 1 master student are working on the molecular communication. Right. I just added this slide for someone who doesn't know anything about the MIMO communications. MIMO stands for the multiple input and multiple output, where both the transmitter and the receiver are equipped with multiple antennas to increase the data rate or to provide the robustness against fading, like the better link reliability. So in the title, I have 2 keywords, molecular stuff and MIMO stuff. I just introduced what MIMO is. But here we have the molecular communication. So to answer that question, I prepared a very short video clip. I believe many of us in this room are aware of the tabletop testbed designed by Andrew Ackford, Weisi, and Nariman. Let's show you. Okay, it works. Okay, we are using the Andrew's platform here. This is kind of the input device. We want to transmit, we want to deliver the 6 alphabets, Y-O-N-S-E-I, our university name. And left side is transmitter, and right side is receiver. And we are not using RF technology to deliver a certain information to the receiver. Rather, we have now chemical signal. So, we still transmitting the information. And finally, you could see we successfully received the information, Y-O-N-S-E-R. So that is the Andrew's the landmark platform. So, but you know that how long does it take to deliver 6 alphabets? 6 alphabet means like 30 bits or so in ASCII code. So it takes about 100 seconds. I just edited some video, but it took 100 seconds means 0.3 bits per second. The question is that, would 0.3 bps be enough for molecular communication? That is the big fundamental question for my research. Yeah, maybe not. That's too slow. Then, how can we increase the data rate? In the classical RF communications, the greater the bandwidth, the higher the data rate. If we have the broad bandwidth, and we could achieve the higher the data rate. But here in the molecular communication, we don't have any bandwidth limitations. We could enjoy the full spectrum. But in that sense, theoretically, we might be able to achieve infinite data rate. But is that true? But you know, the transmitter and the receiver, those nodes should be very cheap. And it's really hard to implement high performance RSI mitigation techniques like WebDM. So it's not possible to transmit with very narrow symbol interval. It causes very severe in a symbol interference. And also, like the commercial sensors like MQ3 that we used for the tabletop test bed, that is a very cheap chemical gas detector. And that sensor is not ideal, which means it has really slow turnover rate. So we need something else. So what can you do to increase the data rate? So again, okay, in the RF communication, the spatial multiplex is a good way to increase the data rate without expanding the bandwidth. So here, just by adding very simple mapper, the serial to parallel mapper, we could transmit the multiple streams over the air. However, okay, for that system, we just need to solve very simple linear equations. Y equals hx plus n. Y is the received signal vector, and h is the channel matrix, and x is input information, and n is noise vector. Then, once we know the h information, the receiver side, we could do geoforcing, or we could do MMSE, we could do ML type solution to decode the information. The assumption is that the receiver has to know the perfect information of h. So, can we apply the same concept to molecular communication? Coherence time is almost zero, because that's a fully random work, random motion. Then, even without Doppler, we are not considering the mobility. So what can we do? That is our fundamental question. So that is the system model. Here we have 2 point source and 1 receiver with 2 receive antennas. With a finite radius here, these are the receive antennas. The spherical antenna, and we have the single body. So here we are considering reflections and also observing by the spherical receiver. So that is a very simple 2x2 MIMO setup. So here, okay, we were trying to have the very practical situation. So for the very simple case like 1 transmitter, there's a point source, 1 receiver, that is the spherical receiver. And we derived the channel characteristic function for that scenario, for the size setup. It's a bit different from what you've seen from the Robert presentation material. And we derived that equation, that formula for the size case. But we cannot directly use that one for MIMO setup, because we have the multiple transmitters and multiple receivers and single body, the reflectors. So we did a lot of simulations to observe, to measure the data. And we also released our fully featured 3-dimensional simulator. We named it Musin. And you could download that one from our website. That's the anyone can use. So we did a lot of simulations for that configuration. And we modified that model function. Here we have the B1, and B2, and B3 to fit the measured data, simulated data. So here, interestingly, we did a lot of simulation with the different parameters, like different distance between the transmitter and receiver, and different distance between 2 received antennas, and also different size of the received antenna. And we got some result here. Interestingly, for the B2 and B3, 2 parameters, they are approximately 0.5, similar to the size case. That is a little bit different, 0.53, 0.5, maybe 6 or so, but still quite reasonable. So we use that equation to model the channel matrix. Oops, sorry. All right, and that is the system setup. We use the binary shift, the concentration shift king, which is over there, 0 for no transmission and 1 for the impulse release. We could have the square waveform or any kind of, okay.
Yeah, could you go back over the channel physics again?
Okay.
I think I missed that. Where am I getting the multiple gains and all that?
I have that slide later, but
Okay.
the thing is that this is the kind of latest formula for the channel characteristics. For the kind of the practical scenario, the point source and sphere receiver observing one. But we cannot use that one. So we want to use that formula.
Yeah, that looks like a first passage time.
That's correct.
Okay.
First passage time that the CDF of the diffusion channel. So that is, we could have the impulse type, or we could have the square, the waveform, even for the of king. But for the second one, we have the large intersymbol interference, of course. So we select that one for the simulation. And we did a lot of simulations with different system parameters to have the more general result. So finally, like the what Chris asked, this is the our system equation. After simple calculation, we have the similar type as in the RF communication. That is the channel matrix, that is the interference, and that is noise, and received signal vector. And here, S11 or S22, they are random variables, like binomial random variable with a single trial with a success probability of Fij. We got that formula from the previous slide. So now we have this similar equation like in the RF communication. So, but here we are also considered in a symbol interference and interlink interference. Okay.
Why was there no cross term in the channel?
That one is in that part.
Oh, sorry.
Right now in our formulation. So the intersymbol interference comes from the previous emission from kind of the desired transmitter. And interlink interference comes from the undesired transmitter, the current time and previous time slots. So we indeed derive the mean and variance of this interference analytically to find the optimal decision threshold. So I'm gonna skip that part. I have the backup slide. So if I have any question, I'm gonna visit that part to share more the information. So here we have the 4 different detection algorithms. The conventional one, we don't have any specific features for the MIMO setup. We just use fixed threshold, which is not related to like any system parameters. And the adaptive thresholding, that is, we could adaptively change the threshold based on the only system parameters, as not changing over the time. Once the receiver knows the system parameters like number of molecules, how many molecules the transmitter will release, that kind of information, then we could find the optimal threshold for that. And also here, we don't have any pilot. So we could think coherence time is almost 0. It's not possible to estimate the channel information at the receiver side. So we could use just the long-term characteristics of that part, like the average numbers. So that is the practical zero forcing to separate or to mitigate interlinking interference as well. And also, we have very, very, very impractical scenario, Gini 80 zero forcing. Suppose we know everything. And we compare this one with our solution. That could be the kind of the upper bound of our system. So we have these 3 equations, and we could skip that part. And that is the very simple the numerical result. We compare the bit error rate performance as a function of the transmit, the number of molecules, and also symbol interval. As we could expect, the fixed threshold ensures the worst performance because the threshold is really important in molecular communication. So here, we just randomly selected number, 0.2 or so. That could be from 0 to 1. So we just selected the 0.2. And interestingly, practical deforcing and adaptive thresholding, they are the equivalent of each other. So we analytically proved that part as well, and we confirmed through numerical result as well. We have exactly the same performance. And we could have kind of quite marginal gap between like the upper bound and our proposed solution. So maybe if you look at that line, 10 to the minus 3, we have maybe 50 or so, quite marginal gap, I would say. So that is kind of the very preliminary results. So this is our new baby. So based on the Andrews platform, we've upgraded to have more the features like we could control the amount of molecules. We could have any shape of the pulse, impulse or Gaussian or whatever. And we have multiple transmitters. I worked a lot to have implement that one. So so we're gonna control by our simple controller Arduino, the chip one, and we could, if you just press this button, and we have something from the first node, and we have another button here to control that one. And now we have the wider one and narrow one. We could control the distance between two antennas. So I plan to have let's see the another solution. We spent about $300 or so to build up that test bed. So we're gonna try to verify the MIMO detection algorithm using this test bed because we have the detection algorithm. So we're gonna implement pretty soon, and we'll see if it really works in practice or not. That is our plan. So let me conclude my talk. We are supposed to finish at 5:30, right?
Yes.
Okay. So let me conclude my talk by just emphasizing, I think the molecular MIMO will play a key role to maximize the data rate for molecular communication. And also here, so far, we have fixed the modulation order, like the binary stuff. It's hard to investigate the multiplexing gain or degree of freedom. So we're gonna also investigate the multiplexing gain of diffusion-based channel. So I hope to have that journal draft pretty soon, in a month or so. I will upload that one to archive, and then if you are interested in the result, I'm gonna share via the email and other stuff. And that is the selected journal publications by our research group. And it's been about 3 years since we started working on this topic. So I believe we have something to share, like channel characteristics and like some practical transmission strategies, like what kind of modulation can we use? And other stuff like the symbol interval optimization or the molecular MIMO stuff. Okay, that's everything I have right now. So I would be more than happy to answer or get any questions.
Is it the same molecular species with each antenna?
I didn't hear it.
Is it the